Hi everyone, welcome to this video on the applications of calculus to kinematics. So kinematics is this idea of, having displacement, velocity, acceleration, that sort of thing. These are all vector quantities, okay? So rather than saying distance, I'm saying displacement. Rather than speed, I'm saying velocity. And well, acceleration is kind of acceleration. But anyway, so the thing is, the idea behind these is that they have a direction. That's what makes them different. So we're going to see a little bit later how, for example, velocity differs from speed, and hopefully the question that we look at will make that fairly obvious. Now, typically in maths, we talk about displacement as x, velocity as v, and acceleration as a. And these are all measured with regard to time. So displacement can be measured in meters or centimeters or kilometers, those kinds of things. Velocity is usually measured in meters per second, and acceleration is measured in meters per second squared. The thing is that there's this link between displacement, velocity, and acceleration. And so what we would normally say is that velocity is the rate of change of displacement. And so knowing that everything we did in differentiation was about rates of change, by differentiating displacement we can get velocity. So what I'm going to do is I'm going to write that we do d dt, differentiate with respect to time. So if we differentiate displacement with respect to time, we get velocity. And we can do the same because acceleration is the rate of change of velocity. So we can differentiate again with respect to time and get acceleration. And so if we can go forward in this process by differentiating, then we can also go backwards in the process by anti-differentiating. So to go from acceleration to velocity, we just anti-differentiate with respect to t, and same going from velocity to displacement, again we would anti-differentiate with respect to t. So I've got an example set up here. We'll just see how this one goes, and what I would say about this question is it's a very typical question for this topic. So a particle moves in a straight line from a fixed origin. Its displacement x meters from the origin at t seconds is given by x equals t squared minus 6t minus 16. Calculate its initial position, write a rule for its velocity and describe its motion when t equals 5. At what time position is the particle at rest? Find the time when the particle is at the origin. Calculate the average speed of the particle in the first 5 seconds and calculate the average velocity of the particle in the first 5 seconds. So, to calculate its initial position, that's really a question about displacement, okay? Because it's saying, what is the displacement when t equals 0, or at the start? So, to do part A, all I'm going to do is say when t equals 0, that's what initial means, we get x equals 0 squared minus 6 times 0 minus 16. So that means that x equals negative 16. And we have to interpret this. So the convention is that if we get a negative answer, it means that the particle is to the left. And if we get a positive answer, it means that the particle is to the right of the origin. Same with velocity. If we had a negative answer, it would mean that the particle is moving to the left. If we had a positive answer, it means the particle is moving to the right. So the particle is 16 meters to the left of the origin. So that is when t equals 0. Part B of this question, write a rule for its velocity and describe its motion when t equals 5. So, to go from displacement to velocity, I need to differentiate. So I'm going to calculate dx dt, differentiating x with respect to time. And that's going to give me 2t minus 6. So I can say that that's equal to v, that is the velocity. And so I've got the rule there for the velocity. I need to describe the motion when t equals 5. So when t equals 5, v equals 2 times 5 minus 6. So v equals 10 minus 6, which is 4 meters per second, because these units are measured in meters and seconds. And so to describe the motion, velocity is positive, which, as I said, means that it's moving to the right. So the particle is moving to the right at 4 meters per second. Okay. Part C. At what time and position is the particle at rest? So, if the particle is at rest, what that means is that the velocity is 0. So we're really finding when v equals 0. And so that means 0 equals 2t minus 6, because that was the rule that we developed for velocity. So I can solve this quite quickly and easily by adding 6 to both sides. 2t equals 6, and then dividing by 2 to get t equals 3. And the question was, at what time and position is the particle at rest? So I know the time is 3. Still need to find the position. So that is, again, talking about displacement. When t equals 3, we get x equals 3 squared. Yeah, I just want to remember that it's minus, right? Yeah, so minus 6 times 3, and then minus 16. So x equals 9 minus 18 minus 16. And so 9 minus 18 is negative 9, and then take away another 16 is going to be negative 25. And that's measured in meters because it's the displacement. So it was negative 25. These bells tell you that. So if x is negative 25, that means the particle is 25 meters to the left of the origin. So the next part, part D, is find the time when the particle is at the origin. So if the particle is at the origin, what that means is that the displacement is 0. So I'll say let x equal 0. And that means 0 equals t squared minus 6t minus 16. And so we need to solve this. And the way that we solve any polynomial is we use the null factor law. So I need to factorize this. 0 equals, and this should factorize nicely. Looking for two numbers that multiply to give negative 16 and add to give negative 6. It should be t minus 8 and t plus 2. So solving this means that t equals 8 and t equals negative 2. The thing is that t equals negative 2 isn't really a reasonable answer because time doesn't go negative. So what I'll say here is reject the negative solution, and so we just get t equals 8. Okay, so that means that after 8 seconds the particle is at the origin. Part E, calculate the average speed of the particle in the first 5 seconds. Right, this is going to be a little bit trickier, and I might actually save this just for the next video because yeah, I think that 9 minutes is enough time on one video. So I'll leave it there and pick it up next time. See you later.